All right, let's get started. So if you went to the TechEd keynote demos, a lot of the initial demos were associated with storage. So I'm assuming a lot of people were excited by that, and this is a follow-up of that. So if you're looking for information on Hyper-V storage, this is your session. If you're looking for anything else, I would suggest consulting the guide. So just a quick introduction. My name is Senthil Rajaram. I'm a program manager in the Hyper-V team. I specifically focus on the storage aspects of the stack. Previous to this, I've worked in the file systems team, the base file systems team, working on NTFS, transactional file systems, cache manager. So the last 10 years, I've been in this particular storage industry. So I've seen things evolve, and the last 2-3 years have been really transformational. It's pretty exciting. So going through how this particular talk is going to flow is we're going to deep dive into some existing and new configurations that are available for storing for Hyper-V storage. What then we will do is dive into virtual. Is it something I said? So what we'll do is dive into some virtual core storage stack improvements that layers on top of these storage configurations. And we'll end with some example configurations that we think are going to be prevalent from customer deployment standpoints. Just because we have enabled a lot of storage options, it's also a confusing standpoint with respect to what do I deploy. So these example storage configurations should help there. So to set context, let's walk you through an exercise that we did earlier this year. So we sent a survey to about 20 IT managers, ranging from large corporations to all the way down to small mom and pop IT shops. And we asked their decision managers, basically their IT managers, what is their number one impediment to increasing virtualization deployments? Very simple question. We wanted to see what's blocking them, actually. Any idea what was least of their concern? Yeah. The surprising part was no one. None of the respondents said CPU was on their minds, which is kind of surprising, a little bit. Next came network. So if you talk about network, we do understand that a lot of these costs are associated with network management, right? It is complex, but we have taken a pretty good stab at it with Windows Server 2012. There's a lot of talks on network virtualization throughout the conference. I encourage you to go and attend that. About 35% of the people said that memory was a constraint. And this was kind of surprising to us, considering all the work that we did in R2 with respect to dynamic memory. We thought we had taken a good stab at that problem. But we pushed and poked the respondents to dive deeper into what was the actual constraint there. And it seems like the problem was with these off-the-shelf servers. And these are really powerful servers that come today, right? Plenty cores, plenty of I/O. And what was happening was that these were not provisioned for large memory. The systems that should have technically 48 gigabytes of memory were just having 16 gigabytes. And once they provisioned that additional memory, things were fine. So, that was relieving, considering the fact that we had invested a lot in R2 in dynamic memory to address the memory constraints. And if you're here, you pretty much know that storage is probably the number one talked about resource constraint from a virtualization management perspective. And this is not surprising, considering that data explosion that's happening across the world. So Forrester sent a survey out in 2007 with respect to IT budget spending on storage, and that was 10% in 2007. That jumped to 17% in 2011. So data explosion is real. It's happening. And once you talk about virtualization, it just accentuates that problem. Because what's happening is that you're taking a whole bunch of systems and then virtualizing it to one particular box. And it puts all the resources within that system under constraint, especially storage. So let me just take a sip. So what I want for you to walk away from this session is to be convinced that Hyper-V and Windows Server 2012 takes a good stab at the storage problem. We are enabling multiple storage configuration options for you. We have made an existing configuration so much better. And these new storage deployment configurations allow you flexible price performance points. You can never talk about performance in the context just by itself. There's a price associated with it. And you can't talk about price without the performance. So what this allows you is to deploy it at the price performance point the workload needs. And with all these storage options, there are two attributes that are seamlessly integrated into it. And these are attributes that are required. These are like absolutely required, foundational for a virtualization workload. High availability and scalability. When I talk about storage options, it's usually about shared storage. And let me give you a little context on why shared storage is important with respect to virtualization, right? One of the key aspects of virtualization is allowing the VMs to be mobile, so being able to live migrate from one system to the other. Now, without shared storage, what you would be forced to do is migrate the huge honking virtual disk files, which will take forever. And shared storage allows us to, not move those virtual hard disks. So you just migrate the VM, the shared storage is there, the VHDs are there, it's visible from another node, and you can restart the VM quickly. And with previous releases, what's happened is that external storage arrays were your only option, right? With Windows Server 2012, we have 3 new options: remote file storage, storage spaces, an abstraction layer built within Windows Server 2012 that you'll be hearing a lot more, which allows you to take a bunch of cheap disks and manufacture pools and spaces on top of it. Another technology called clustered PCI RAID. Traditionally, in the past, you would never be able to use host-based RAID in a clustered configuration. We've worked with our partners to enable that. So with all these options, we believe that we'll take a good stab at the price performance equations for your deployments. And we'll dive into each one of these in detail. So the first thing that I want to cover is how do I make your existing hardware investments better with Windows Server 2012, right? One of the first features that we talked about is virtual fiber channel. Virtual fiber channel allows you to surface the virtual fiber fiber channel into the guest. So this is really critical if you think about high I/O workloads like SQL. They just want direct access to the high-performance disk. They don't want any virtualization stack to be there. And by surfacing these particular SAN disks directly up to the VM guest without any virtualization layer, we kind of take a stab at that problem. This also allows us to do guest clustering. Previously, the only way you could guest cluster your apps is through iSCSI disk. Now you can use your existing hardware investments through SAN to have your virtualized workloads kind of be guest clustered. And there are a few key management software out there that needs direct access to the SAN fabric to perform management operations. And previously, the way you would connect a fiber channel disk is as a pass-through is putting it to the host, offlining it, and then connecting as a pass-through disk, which would filter out all these management CDBs that flow from the guest to the host. But now with direct access to the VM fabric, these management apps can be virtualized and can perform their management functions on the SAN. How do we enable this particular technology? We use something of an industry standard called N-port I/O virtualization technology. It's been around for a while. And what this allows is taking a HPA and splitting up into virtual functions. And each of these virtual functions is manifested into the guest as a virtual HBA, right? We have worked with the hard HBA manufacturers to kind of seamlessly integrate the NPIV feature. So you would need an NPIV-capable HBA, and as long as you have that, Hyper-V host will recognize it and allow you to surface those virtual functions into the guest as virtual HBAs. For this to be supported, you obviously need a Windows Server 2012 system, but you also need an NPIV-capable HBA. Please contact your HBA vendors to see what particular systems support NPIV. And the guest support goes as far back as 2008. Anything prior to that, we didn't feel that it was a necessary investment. Your ICs will be automatically updated and will provide you this functionality. And one of the most exciting things about this particular configuration is the fact that live migration just seamlessly works, right? So you want that particular feature. You don't want to say, hey, now I have this particular configuration, but I can't do live migration. So that's just not an option. Let's just take a look at how we actually do this, live migration. So we have a VM on the source, right? And this is how it's going to be configured from the virtual fiber channel. You see you have a virtual SAN, and it has 2 worldwide names associated with it. And there's a good reason for that, right? There's only one worldwide name that's being used at a particular point in time. The second one is used for specifically the purposes of live migration. So, on the source, worldwide port name A is being actively used, and the shadow port name B is kept, and its use will be during live migration, right? So let's assume that you're starting to live migrate this particular VM. So what happens initially is that there's a temporary VM created on the destination. The temporary VM's fabric is instantiated with the worldwide port name B, which is the shadow port name associated with that virtual fiber channel adapter. With this virtual fiber channel adapter, the shadow VM performs a discovery on the secondary node. And the reason why you want to do this is because the port logins and discovery is actually a time-consuming operation. And with live migration, you want that guarantee that your blackout time is as low as possible. You want to be doing this during the brownout times. And this is the reason why the port name B is instantiated and done that. So once the discovery happens and everything is hunky-dory, what happens is that slowly we start quiescing the source VMs. We copy the memory, we copy any other files. We limit the queue depth to 1 so that the IOs are throttled and we are able to catch up and move those particular IOs onto the destination side. We pause the source VMs. We change the temporary one to a permanent one on the destination. And we log out of the source fabric and delete the particular VM. And the VM on the destination is up and running. So let's just take a live demo look at this particular feature. So what you have here is, I apologize for the screen resolution. This was the problem that I was mentioning. So what you have here is, 2 Hyper-V nodes. They're clustered. Obviously, as a sequel, you want clustering both at the Hyper-V host level as well as the guest level for high availability reasons. If the host machine goes, then you have the instance moving to the other node. And if the guest cluster comes down, then it's instantiated, and SQL takes care of that at the app level. So what we have here is a system that's exactly doing that. We have Two particular nodes. One is running SQL A, and the other is running SQL B. And if I go back to the SQL A server, I go back to connect to it, you see that it's got the SQL instances running within it. And it's got the fiber channel disk attached to it from the port. And let me just go back and take a look at the settings for you. So as I mentioned before, there's a fiber channel A and there's a fiber channel B. There are two particular disks for the SQL cluster to be, SQL app to be using. One is for its database and the other for the log. And as you see, each of these have, two particular worldwide names. So what I'm going to be doing here is instantiating the SQL workload. I'm going to be generating a lot of I/O traffic both on the primary as well as the secondary. As you see, it's running about like 1,500 transactions a second. What I'm going to do is drain this particular node. And you will see that the SQL A workload still keeps running, but at a certain point, it's just going to slow down and start moving to the other node without dropping any of the transactions. This is key. And you'll see the live migrate is happening here. It's about 65% complete. And at a certain point, it's just going to pause, and it's completely moved over to the other node. See? Live migration is complete. Now it's running on TechEd 4 without it dropping any transactions. I'm going to quickly stop that. So the next feature that we talk about within your existing SAN infrastructure is something called unmap. How many of you here know about trim and unmap? All right, so a few. Let me give you a little bit background on why this particular command is actually used in the industry. So back in Windows 7 timeframe, there was a lot of talk about SSDs, right? And SSDs have this particular problem of a limited write cycles. So each of these particular cells had a limited number of writes that you can do before they die. And one of the things that the SSD manufacturers wanted to do was spread out the lifetimes of all the cells so that not one part of the disk goes out earlier than the other one. And this mechanism that they do is called wear leveling. They distribute the writes equally to all the pages in the SSD. And one of the key requirements for the wear leveling mechanism is the fact that you need a lot of spare pages for it to be effective. So they came to us in Windows 7 timeframe, and we worked with them to implement something called trim, which is the ATA side of the command, which allows the storage stack, the file system, the app, or anything to tell the actual physical disk that, hey, I'm done using these particular clusters, right? Go use it for something else till I come back and request it. Now, if you take this particular mechanism and push it out to SAN, where thin provisioning is prevalent, right? And this is exactly the command that makes sense there, too. So now, unmap is the SCSI equivalent of trim, which is the T10 committee. So basically, they perform the same attributes, right? They just allow the app to send down unused cluster information down to the storage. And for a thin provisioning system, that makes a lot of sense. But if you take this particular feature and translate it into the virtual storage stack, there are efficiencies both at the virtual layer. So think about it from a VHD perspective, right? I'm getting told that a particular block is now not in use. What am I going to do? I'm going to be smart about it. Anytime there's a need for an allocation of a block, now I can use that particular allocation instead of going and allocating a new block. There's efficiencies at the physical layer too. As I mentioned before, thin provisioning is that much more efficient because of this communication down. So we have seamlessly integrated this particular feature all the way from the guest down to the virtual disk layer and down to the physical disk layer. And what you're going to see is that the virtual disks are going to be consuming lesser space with Windows Server 2012. Now, we've made a key decision to limit the support for trim and unmap only on the new virtual hard disk format. And there's a good reason for it, because the state information that needs to be persisted when a particular block is communicated as free is available only in VHDX, because this format has been designed from the ground up. We couldn't retrofit that in VHDs. We've also made a decision that it makes sense only for the virtual SCSI or the virtual fiber channel adapters. Let's take a quick look at a demo that talks about this unmap integration. So what we have here is two VMs. One is connected to a VHD. And since VHDs don't have the support for trim, it becomes a perfect foil for demonstrating this feature in contrast. And this one is connected to VHDX, right? So what I'm doing here is trying to work with the existing resolution. So, all right. So now I have a counter here that monitors the size of these particular VHD files as I perform certain operations on them. As you notice that the size of the VHDX file is slightly bigger than the size of the VHD. There are a couple of reasons for that. The default block size for VHDs are slightly larger, 32 MB in the case of VHDX, and as you know, for VHD, it's 2 megabytes. We also do pre-allocate certain space in VHDX so that we can quickly serve those requests up, which we did not do with VHDs. So now what I'm going to do is copy a big, huge file onto the VHDX disk. And I'll do the same on the VHD file. As you can see, both of these allocate new blocks, about 1 gigabyte, and they grow in size as you would expect. There's nothing magic here. And once this particular operation completes, we'll do a delete operation. As you would delete a file, those particular NTFS is going to know that these files' space is going to be released, and it's going to send down trim information, trim and unmap information down to the virtual disk stack and down to the SAN, right? So as you can see now, as you expect, VHDX has grown by 1 gigabyte, VHD has grown by 1 gigabyte. Now let's go and delete this particular file. I have to be careful here to permanently delete the file instead of it going to the recycle bin. And we'll do the same with VHD. Now, NTFS has this checkpointing mechanism which sends down these particular information every 5 minutes. They don't think about this feature to make my demo life easier. So let's do something to make that easier, right? So I'm going to run this new feature called Optimize. It's basically defrag, but it's more than defrag. It does a whole bunch of information, including sending down trims as and when needed, right? So this is a PowerShell script that allows me to basically optimize, drive data X. that operation is complete. I'm going to go do that to the volume on VHDX. That completes. Now, we'll do the same operation. We'll move the same file onto the disk again, but to a different volume on the same disk. I just want to be sure that I copy down to the right. As you would expect, the VHD size is going to keep increasing, right? Because it doesn't know that, it doesn't have the trim support. But with VHDX, you see that it's not going to be using any new space. Why? Because previously, during the delete, it was communicated saying that, hey, you have this 1 gigabyte of free space now. And VHDX, the storage layer, is smart enough to know that and reuse it for a future allocation, even though it's on a different volume, but it's on the same disk. This is a disk-level feature. It doesn't stop there. Right? I'm going to go back and delete this file again. What do I need to do? I need to run optimize. Once that is complete, I'm going to shut down these 2 VMs to show you how those pre-allocated blocks are actually released. So let's take a look at shutting down these 2 VMs. So as soon as the VMs turn off, the VHDX is dismounted, right? From a host perspective, it knows that it doesn't need that VHDX for anything. So all that information associated with saving it for a future allocation is released. The VHDX file is shrunk. So literally, from just one meta operation of a create and a delete cycle, you saw about 1.5 gigabytes of saving. Multiply this across your VM, the number of VMs you have, right? Think about the savings. Maybe this is a manufactured scenario. You don't copy and delete 1 gigabyte files. But what the concept that's presented here is pretty powerful. If you think about the number of VMs that you have in your data center, and each of them saving, maybe a few gigabytes here, a few gigabytes there, it quickly adds up to a lot of saving. Again, that doesn't stop there. I want to take it to the next level. I want to show you how the SANs can benefit from this too. So now we have a VHDX file that's stored on a SAN. And now I'm going to show you, I'm going to do the same set of operations on this particular VM. But at this particular, in this particular demo, we're going to monitor the SAN space that is being used by this VHDX file. Like I said, right, there's an storage optimization at the virtual disk layer, and there's a storage optimization at the physical layer. And this particular demo shows you how the physical disk layer is going to benefit from this feature. So let's go to this particular VM. Sorry. Operating at a smaller resolution just slows me down. I really apologize for this. All right, for this demo, we're just going to use a script just to speed things up. Right, what I'm going to do is All right, so what I'm going to do here is copy the file, big file, onto the local disk X, which is basically the VHDX, right? You see the file is getting copied. And we are forcing the file system to flush it down to the particular disk, right? So, whoa. What you see is that the VHDX file has grown by a gigabyte, right? It's gone from just about 290 MB all the way to, roughly about 1,300. And you see the use SAN space has also jumped, obviously, because that particular disk blocks are actually getting stored on the SAN. Now we're going to actually remove that item. And we're going to do the optimize to force those particular retrims to happen down. And notice the use SAN space. There you go. So what's happened here is that those particular trims have flown down all the way down to the physical disk and communicated that the 1 gigabyte is free for it to use it for whatever purposes. So it's just reclaimed it. And what we do now is shut down this particular VM, and you'll see that the VHD space also drops. There you go. So what this demo does is kind of show you that space is being optimally used both at the physical disk layer as well as the virtual disk layer. I'm going to shut these off. So let's talk about, if you went to the keynote demo, Jeff kind of showed off a feature called ODX, right? Basically offloaded data transfer. And he basically copied a 10 gig file across from 2 different shares in about 10 seconds. And there's a reason for thinking about offloaded data transfers. SANs inherently are really powerful, right? They have a lot of storage processing power in their backend, and they're basically begging for work. So there are certain operations, especially like copy, that could be done in a much better way. Let's talk about the existing storage model, right? The traditional data copy model is where a server issues a read down to the disk. It gets a whole big, huge honking chunk of data back into its memory, and that data is taken and sent back down to the same SAN again. This is really inefficient if you think about it, right? What it does, it consumes CPU as well as host CPU as well as memory. And these two are critical resources that define the scale aspects of, consolidation scale aspects. It also increases the storage traffic in the fabric, which is also another critical aspect of, reducing IOPS. It's inefficient for the SAN. Technically, a SAN could think of this as a dedupe, communication, right? Saying, copy this particular data. Technically, it could just, have some pointer magic done in the background and call the copy done if it was provided that opportunity. And offloaded data transfer does exactly that. It addresses all these problems. So the data copy model is pretty similar. So, you issue a read down to the SAN, and instead of it sending data back, it sends a token representing that particular data. And we take this particular token and send it down to the destination disk. The SAN completes the copy from, whatever metrics, wherever it needs to be copied from, to its destination, and sends back a confirmation. So you've just literally taken away the need for the host CPU and memory to be used for this particular purposes of copy. And if you think about virtualization workloads, it does involve large data copies and large data movements. This is perfect for virtualization workloads. There are certain meta operations, as we call, which you use to perform operations like merge, mirror, which is the basis for moving virtual hard disks from one place to another, which will be covered in a different session. There's another demo that I talk about with respect to using this particular feature for writing a whole bunch of zeros down to the disk. Instead of me manufacturing data in the buffer, which is all zeros, and sending it down to the SAN, I can just communicate now using this zero token down to the disk saying manufacture these zero regions. And the SAN can really efficiently do them. I have a demo on that. And we have also plumbed this all the way to the guest. So the guest application, if it issues copy offloaded commands, these are translated all the way down to the disk. And these are plumbed all the way down to the SMB stack too. So technically, you could think of copying a file from a file share down to the virtual hard disk that's stored on the same SAN. And all this is done via the copy file, the offloaded copy mechanism. You wouldn't see any network or data being copied around. The SAN does it underneath. Really powerful. So let's take a look at a demo for ODX integration. So what I have here is I'm trying to set up a race, right? How many people here have created 100 gigabyte fixed VHD files? Whoa, painful. Tell me how long you usually have to wait. At least multiple coffee trips, right? So what I have here is a race between trying to create a 100 gigabyte fixed VHD on an offload-enabled path and a non-offload-enabled path, right? Let's see how long it takes. I'm going to run the script. It's doing some pre-staging, just making sure that they both start on the same time. It's ready to go, and you see, boom, just about 2 seconds. Somebody remind me to check on how much progress the non-offloaded one has made by the end of the presentation. But I'm pretty sure it's not going to get done. So that's the power of offloaded. And we could think about many other features that the SANs could do better. And probably in the future, the storage stack can provide that information down to the SAN to do the storage functions much more efficiently. So we've talked about two basic functions, copy as well as creating zeros, that we have completely plumbed all the way from the storage stack, from the physical as well as the virtual. So if you have a SAN, technically, Windows Server 2012 is a no-brainer. With all these stellar features with respect to virtual fiber channel, trim, unmap, you're just going to leverage it so much better for your workload. But let's talk about some new storage options, right? As I mentioned before, file storage is something that we have introduced as support for your virtualization workloads. Let me give you a little bit of background on the file storage support story. Obviously, this has been something that's been asked forever. Ever since Hyper-V V1, people have asked for remote file storage support. We actually took a good stab at it during the R2 as well as the Windows 7 timeframe. And it kind of sort of worked with the old protocol, the 2.1 protocol. But there were enough holes in the overall virtualization scenarios, including mobility, that kind of was not enough. It was just not good enough. We shelved that, and we worked with the SMB team to kind of feed in our requirements from a virtualization perspective for it to be a seamless storage option, and as good as a storage option as the local one. And there's a whole talk dedicated to Hyper-V over SMB, but I want to dive into a little bit of the challenges with respect to the virtualization workflows that we've kind of addressed using certain SMB 3.0 features. Not only does your existing scenarios work, everything, your live migration, your second-level page, all the features that you get out of the local system, you get out of the remote system too. Not only that, it allows us to create new scenarios based on the file server support. So there's another session that talks about, building flexible Hyper-V environment, and this is entirely based on the fact that you don't need shared storage now to move VMs around. You could technically create a SMB share on the destination host and move the VHDs, as I was talking about. Painfully slow, but you could still get it done, right? You've just taken away the dependency from the need for shared storage here. So you can talk about shared nothing live migration. You could talk about cross-cluster live migration. All these features depend upon the SMB 3.0 support. And even though we don't actively block the previous version of the protocol, we don't support it for obvious reasons. We want your experience to be seamless, and we don't want our support center to be inundated with calls. So let's talk about, when you talk about network topologies, there are various failure points that could happen, right? More so than the local systems. And you could talk about the network failures as well as the machine failures. But we wanted to address them to ensure that high availability is always guaranteed throughout this particular configuration. The first kind of failure that usually happens in a network-based topology is someone clumsy like me walking around in the data center, tripping over the network wire. How many people here have done that? I do it in my office. But at least I'm smart enough to realize that and plug it back in, right? So that works. With SMB 3.0, there's a feature called resiliency that allows me to survive this particular failure. So consider this. There's Hyper-V host talking to a file share. The VM's hosted on it. Everything's fine and normal. Now there's a temporary disconnect. With this particular resiliency feature, what happens is that the SMB client on the Hyper-V host, as well as the SMB server on the file server, is smart enough to start caching the state of the system. Right? They hold on to this particular state for roughly 60 seconds, waiting for that reconnection to happen. And when that reconnection happens, everything is reestablished, I/O backed up is flowed across, everything catches up, and you're hunky-dory. The next class of failures is the permanent network disconnection failures, right? We are good, but we cannot solve that problem without the hardware support. We cannot do this in software. So, but it's really not that uncommon. If you think about it, today's servers, very common to have, dual network cards with dual ports. So it's not that onerous for us to ask you to have dual paths to the file share if you're interested in protecting your workloads for high availability. So we have this. Let's assume that there was a permanent disconnect to one of the one of the network paths. We have this feature called multi-channel, which allows us to transparently survive this failure. What it also allows is that both of these paths are being used in an active-active configuration. So you would have a demo in the Hyper-V over SMB session where you would literally be getting the maximum throughput through these two paths. And then when the failover happens, it's only one direction, right? You're communicating out. It's not a duplex. So the question was whether it was bidirectionally. So SMB protocol, you're just communicating out. So the connections and the handles fail over to the other one, and your application receives absolutely no I/O errors. Let's talk about machine failures, right? Consider the case where you have a file share being hosted on a particular file server, and that file server is actually clustered, right? If you need to survive machine failures, you need to talk about a clustered system. In this case, the file server is clustered. Now, there's a feature called continuous availability. This is a foundational feature for SMB, right? And you heard about this in the keynote too. So what happens here is that, let's assume that there was a failover, the file server node A failed. That file share is automatically moved over to the new node. All the state that was needed for connections to be reestablished was persisted to the disk. The new node picks it up, replays all the information, instantiates the shares, and the SMB front end makes those connections to the new file server location, the file shared location. This happens transparently. And this has been tested at scale, thousands of file handles being opened and failed over with respect to a particular file share. What about Hyper-V node failures? Right? There shouldn't be any problem here. Right? But what happens is that in the case that the Hyper-V node fails over, the VM moves over to the other node and tries to open the same files that were opened from the previous node. Now, think about the case for resiliency, right? The resiliency mechanism is actually holding on to the state, expecting the previous node to connect to it. And it has no way of knowing that the new open that's coming in is from the same instance of the app. And that's what cluster client failover allows us to do. It allows Hyper-V as an application to communicate out to the file share, saying that I'm a particular instance, in this case, a VM, and through the VM GUID, this is a particular instance of an open. And even when I fail over, I'm going to use the same VM GUID, right? And I'm going to try to open that particular file again. But in this case, the file server has the context into shooting down the stale handles because it knows that it is the same instance of the app requesting access to that files. If it wasn't for this, you would have to wait 60 seconds for that VMs to come up. And that was just not an acceptable option, right? So the stale handles are shot down, state is brought back up, and VMs can quickly fail over. Another interesting workflow, an important workflow, just not an interesting workflow, is backup, host-based backup particularly. Guest-based backup is just not an option considering how much management overhead there is associated with that particular solution. And today, with respect to the local configuration, we have this component called virtual shadow service, which is used to take the snapshot of the local volume. And what we have done with this particular feature called remote VSS is we have had the same mechanism flow over SMB. So from the perspective of a backup application, there is no change. So a backup agent requests a VSS service of a backup. That particular request is translated to the file share, where the file share is snapshotted and presented to the host, and the backup application then works on it. So seamlessly integrated. There's absolutely no impact. Now, talking about performance, we wanted a performance goal of allowing you to have a configuration that works just as well as the local one, if you have the right kind of hardware. There is this new hardware technology called RDMA, remote DMA. Basically, there are some network cards that are out there that support this particular feature, which allows the CPU to be removed from the process of processing the network packets. And this is kind of key, again, right? As I go back and talk about reducing the tax on your host CPU and memory or any other resource, it just allows for higher consolidation. So remote DMA, not only does it increase the performance of the network traffic, but also allows the host to scale up much better. So there's a whole talk on this, which is in the related content section that I highly advise you to attend. There was a previous mention of multi-channel. I just want to reiterate the fact that if you have dual network paths to your file share, it's just going to be using it in an active mode and that much higher performance. I just want to have a quick point to note with respect to setup and administration, because this is a gotcha. And I know people have already run into it here. Management functions, like Brad mentioned in his keynote, there are 2,400 PowerShell commandlets. A huge part of it's both SMB as well as Hyper-V commandlets. Anything that you can do from a UI, you can do it through a PowerShell commandlet. One of the key requirements while you're setting up a file share for hosting VM files is that the right permissions are set. And you need to have the Hyper-V host machine account full access to the file share, as well as the NTFS folders backing the file share on the file server. This is really key to understand. How many people have already tried to instantiate a VM in Windows Server 2012 and ran into this particular issue that they didn't have? There you go. So you really need to be aware of this. This is the most common failure mode that you'll hit when you're trying to instantiate a VM on the file share. And the reason for this is that every VM has a VM security identifier, right? And that works well in the context of a local system. But when you translate that across a machine boundary, you're running into this problem of it's not understood by the remote system unless you have an AD group associated with it. So once it's translated across the machine boundary, it gets converted into the host machine security identifier. And that's the reason why you would need the file share to have the Hyper-V host machine accounts for full access. Let's move on to a different storage option. With SMB, you've seen that it's seamlessly integrated into the workflow. It provides all the high availability requirements needed from a virtualization perspective. Storage spaces is a pretty interesting feature, and it's part of the Windows Server 2012. It's been implemented by the core storage system. And what it allows you to do is it creates a storage abstraction layer that takes a whole bunch of just cheap disk and creates an abstraction called a pool. And within that abstraction, you could carve up disk, virtual disk in this case, called spaces, that to the system, they just look like a regular disk. Right? Pretty much if you're used to the model of a SAN, that's what they do. They have all these various disks associated with it. You carve up pools, and then you carve up LUNs associated with it. Storage spaces allows you to do just the same abstractions, but with cheap disk, right? Just direct attached disk. And it provides interesting attributes to it. So as I mentioned before, a pool, you're creating an abstraction of a large disk just from small individual disks. It also gives you the ability to thin provision them, which means that you could technically create a pool which is much larger in size than the sum capacity that you have with respect to physical spindles. And as soon as you attach, space is running low, you attach a new disk, storage spaces recognizes that and starts consuming it, just-in-time provisioning. And the last one attribute is pretty key. So you could set up a space to have a resiliency attribute. You could think about it as, simple space, which allows you to stripe the data across multiple disks. You could think about mirrored space, which allows you to create a two-way or a three-way mirror, or a parity disk. You just created a parity system. So now, storage spaces for a standalone system is interesting, but let's talk about where it plays in the virtualization context, right? You absolutely need cluster support for spaces for it to be viable, to be used in a virtualization scenario. And both simple as well as mirrored spaces are supported by cluster. It's just not ready for parity spaces. Just want to call that out. For simple space, you have the concept of direct I/O from all nodes. So it's presented as read-write to both nodes, just as a regular disk would do from a CSV perspective. Mirrored has got a gotcha. From the primary owning node, each space has got an owning node. You have direct access. But when you try to access that particular mirrored space from a different node that's not owned, you get CSV redirection, right? So it's presented through the CSV layer, but storage traffic is hijacked through the CSV layer to the other node, the owning node. This is a limitation that you need to be aware of if you're provisioning and you plan to get into this mode of running a VM on a mirrored space from a non-owning node. For whatever reason, you're migrating a VM onto a different node for load balancing your CPU or memory. So you just have to be aware of it. And our guidance is to use, in this case, low latency, high throughput network devices like RDMA or 10 gig E for the CSV management channel, the cluster management channel. Let's talk about the next storage option. It's called clustered PCI RAID. Forever now, we've been giving out this message saying that please do not use host-based, RAID systems in clusters for good reasons. We never had the tight solution where you would not allow these particular RAID cards to stamp over each other. Now, what we have done with Windows Server 2012 is remove that limitation. LSI, we worked with LSI and a few other partners to implement this solution where you have these PCI RAID cards, host-based RAID cards, that talk to each other. through a SAS channel, right there, to be smart about which node owns what particular disk and make sure that during a failover, the particular LUN migrates over to the other surviving node. All this without any impact to your write or resiliency guarantees. So if you do have a disk failure, you're protected through normal RAID mechanisms. And if you have a machine failure, then that particular LUN is failed over to the other node, and everything is just fine. VM would move to the other node. It would have access to the disk. And the key here is to realize the fact that this particular abstraction, again, uses shared SAS JBODs, cheap JBODs, to almost give you the abstraction of an high-end SAN. And there are systems that are being put into place where you have these PCI RAID cards actually being able to cache data. So if you think about LSI, Mega RAID, and HA DAS, you have capabilities to cache data when it's flowing down. And today it's only read. They're working on write caching too. So incredible innovation through Microsoft as well as its partners to reduce the cost of storage. So I'm just going to quickly touch upon, now we've done the core the storage options. I'm going to quickly run through the virtual base core storage stack improvements that layers on top of this, all these notions. And the first one I want to touch upon is something that we made mention of with respect to VHDX. Now, with VHDs, they've served us well for the last 15 years. They've been a great format. They've served, I think it was written in 1995 and came to Microsoft through an acquisition of Connectix. But with, when we talk about starting to virtualize large SQL databases, 2 terabytes as a limit was just not going to cut it. We needed a new format to address that. So what we did with this particular new format is we looked at all the features that, is going to future-proof the virtual hard disk format going forward. And one of the first things that we did was remove the 2 terabyte limitation. So you can scale a dynamic VHD and a differencing VHDX all the way to 64 terabytes. This is 32 times greater than what our competitors can provide. Incredible scale. There is also an internal log within the VHDX format that's going to protect the VHDX file from getting corrupted when there's a power failure on the Hyper-V host. So this is really important. You have a system in place that's going to ensure that your virtual hard disk survives a power failure crash. I just want to make sure that you understand the fact that we're not trying to protect the data within the VHDX. That's taken care of by the file system and the disk stack within the VHD, right? What we are trying to do is protect the VHDX file from getting corrupted. And the internal log is doing just that. We've also future-proofed this from the perspective of supporting some new kinds of disks that are coming, with large sector. Instead of the traditional 512 bytes, now they have 4K. And with the VHD format, there were problems that we will just talk about in the next slide. But what I want to communicate here is that, one of the advantages of designing the format from ground up is that everything is nicely aligned in megabyte boundaries. So we also have enhanced perf. One of the key requirements that storage administrators told us is that, hey, we like that you can have block sizes of 512 KB and 2 megabytes, but there are applications that do IOs in larger chunks, and that's what we did with VHDX. We now support block sizes all the way down from 1 megabyte all the way to 256 megabytes. So it allows the storage admin to tune the VHDX to meet up with the virtualization workload needs. The last feature that I want to call out is something interesting to virtualization software management vendors, right? With what they used to do for storing information related to that VHD file is to have an off-band mechanism. Let's say that they wanted to always know what version of the OS is installed within it. They always used to have an off-band mechanism to carry that information around. With VHDX, they can actually embed that information through small key value pairs to say, with this particular key, I'm going to have Windows 7 or whatever OS version is it embedded within the file. And when the file moves, that particular information is carried along with it. They can use that particular key to query that VHDX file to get the OS version that they were previously stored within that. They don't need to crack open the VHDX file, go look at certain Windows directory to figure out what OS version is it. Now, at the time of provisioning, they can store this information and get it back anywhere and any place they choose to do so. Just a quick slides on performance. You can see that what I want to call out, is that for a really stressed out system with a queue depth of 16, you could see that the fixed VHD scales as well as fixed VHDX scales as well as your regular pass-through disk. And the key innovation here is that there's literally no difference between a pass-through disk as well as a fixed VHDX versus a dynamic VHDX. We have also improved the performance associated with differencing VHDX. It's 10 times better for a 32 KB random write scenario. For another workload characteristics of a sequential write, in this case, a 1 megabyte sequential write, you see that the VHDX, both dynamic and differencing, match up almost as close to as pass-through disk. Not only we have enhanced the resiliency story, but we have given you performance better than it. Resiliency comes with a cost with respect to logging your metastructures and whatnot. But we have just made it smarter and ensured that your performance is that much better with VHDX. So use VHDX wherever it's possible. The only caveat is the fact that VHDX is going to be supported from Windows Server 2012 onwards. It doesn't have, you can't take this down to a down-level system. Let's talk quickly about large sector disk support. So if you traditionally go down to MediaMart or Best Buy in the US, if you buy a 3 terabyte disk today or a 4 terabyte disk, what you're going to get is a large sector disk. And what this means is traditionally what the disk manufacturers used to have a sector size of 512 bytes. They're moving away from that and having 4 kilobytes as the sector size. And this allows them manufacturing efficiencies. Disk manufacturers work on pennies, so any manufacturing efficiencies that they can get, they're going to jump on. And they've been threatening this 4K sector size disk for a long time, and they finally made it true. So today, if you go out and buy a really large 3 terabyte disk, in all probability, you are going to get a large sector disk. And there are two kinds of large sector disk. One is an emulated 512E. So what this does, it abstracts a 512 byte layer onto the application, but internally it does everything in terms of 4K. And this is required because not all applications and systems can deal with just a pure 4K disk. So where they would traditionally like to go is a native 4K disk, which means that there is no abstraction layer. You have to send IOs that are aligned to 4K. Otherwise, it's just going to reject it. So as I mentioned before, with VHDs, there was a performance problem with large sector disk. And the reason for this is that the VHD format itself has 512 byte structures within it. So, and there are few of them. Sector bitmap is one of them. The header, the footer, and the parent locators are structures within the VHD that are 512 byte aligned. But the most problematic of all this is the sector bitmap. And the sector bitmap is this 512 byte chunk of data right in front of the payload block data. So if you allocate 2 megabyte, there's a 512 byte right in front of it, which kind of says which sectors in that particular block are being used or not block. But that kind of creates a problem. So even if you send a 4K aligned I/O to the virtual disk, that particular 512 byte shifts it. So every single access to that block now is shifted out by 512 bytes. So there's a read, modify, write penalty associated with servicing disk. And the way the 512B disk service these 512 byte access is by this particular mechanism called read, modify, write. They have to read from the physical device at 4K, modify that 512 byte of that associated 4K, and write it down. And we have seen anywhere between 30 to 50% performance penalty associated. So with Windows Server 2012, what we have done is we have aligned it. We have made these structures 4K aligned, so we've just done padding. This is not rocket science, but we had to do it just to ensure that there was no performance penalty. I just want to point out the fact that if you bring a VHD from a down-level system onto Windows Server 2012, it's not going to be aligned for you. You'd have to manually go through the process of aligning it by creating a new VHD. I just want to point out the performance impacts of this alignment, right? So you see there's like almost 6,000% performance improvement for a 64 KB sequential write workload. And that's the case for, for a 8 KB random write scenario, you're almost reaching the performance of the raw disk. What about native 4K disk? Previously, we did not support native 4K disks because of the fact that, as an application for the virtual disk, we used to surface out a logical sector size because we are a disk layer. We have a logical sector size and a physical sector size of VHD. And VHDs could only manifest themselves as a 512 byte device. So applications using the virtual hard disk used to send down 512 byte, writes. And we needed to implement a software read modified layer in our stack to ensure that any of these particular disk configurations could actually work on a physical 4K device. Obviously, there's a performance penalty because any read modify write is performance intensive. But if your system and your application can deal with native 4K devices, then we suggest that you use 4K logical VHDX. VHDX has the capability to manifest itself as a 512 byte disk, a 512E disk, or just a pure 4K disk. So, since we're running short of time, so there are a whole bunch of meta operations that I want to talk about we have made online, right? So in the past, there were anytime you needed to do any of these certain meta operations, you would need to bring the VM down, and you would need to, perform those meta operations. Now we have enabled, some of those meta operations to be done while the VM is on, because we want to ensure that you don't have to go through the process of, managing the downtime and to perform these operations. So you can now delete snapshots and instantly reclaim the space associated with those particular snapshots. So previously, this was one of the major complaints that people had with respect to, I had a demo, but since we're running short of time, I'm going to skip over that. You can instantly reclaim that particular space associated with the deleted snapshot file. Another key aspect is mirroring of these virtual disks. So in case you have to move the virtual disk from LUN A to LUN B, now you can do that through something called online mirror. And there's a separate, like I mentioned before, the VM mobility talk that's going to cover this. We also have another meta operation called set parent, which allows you to, on the fly, change the parent associated with a virtual disk. And this is really key because if you think about it, if you're running from a differencing VHDX file locally, that's pointing to a remote VHD. But if you want to suddenly increase the performance profile of this particular VM, you could do so by copying that VHDX file down and then setting the parent of it on the fly without bringing the VM down. Sorry, I'm going to skip over the demo. With respect to I/O scaling, previously I/O scaling, it was purely limited by the fact that there used to be only one channel between the host and the guest. With 4 VPs, when you talk about high I/O load, probably that was not a limitation. But when you talk about 64 VPs trying to slam IOs, that was one of the bottlenecks. Another key aspect of that was that VP0, the first VP, was the one that used to be targeted as the IO completion virtual processor for the interrupts. Again, maybe not a problem with 4 VP support, but when you start talking about scaling up for 64 VPs, then pegging one of those VPs just for IO completion turned out to be the bottleneck. Another important scalability aspect was the fact that the queue depths associated with a virtual adapter was shared across all the devices that were connected to it. So we have removed all these limitations now with Windows Server 2012. And this was the reason why you saw the 1 million IOPS being hit. Like all exactly all these 3 features pooled in to make that million IOPS possible. So what you really have with Windows Server 2012 is not being limited by the virtual storage stack limitations. Whatever IOPS you can get from the host stack, you could literally plumb it through the VM. A few other key features that I want to quickly touch upon is the fact that there's now CSV implements something called a read cache. So this is a cache at the block level, which is very effective for bootstorm cases. So you have one particular virtual hard disk file, a parent, out of which you create a bunch of VMs. And when you're booting, that particular parent disk is now the bottleneck because it's trying to you have every single access going down to the disk. With this particular block cache feature, CSV caches that particular frequently used blocks. So it's really effective. So please do look into this particular feature when you're, sorry. There's another feature called the dedupe. There was dedupe previously in Windows Server, which was single instancing SOAR. That worked at a file level. With Windows Server 2012, you have the ability to do it at a block level. This is really interesting for static VHD files, right? If you think about the classic library server, you have tons of VHDs there that spans multiple OS versions. But what we have found is that they all have the common set of blocks because all these DLLs and everything else, and they dedupe really well. And I've seen where a library server goes from 1 terabyte all the way down to 40 gigabytes, right? You have that much potential for saving. The one key attribute that I want to point out is that this is not for live VM VHDs. Please do not dedupe VHDs that you're currently running on. That is not ready for prime time and is not supported. Soon, one of these days. I just want to quickly touch upon those example configurations. We have about 2.5 minutes left, but I'm free to walk you through this, post the or at the virtualization booth. So one of the things that we always mention is if you have an existing SAN configuration, Windows Server 2012 is a no-brainer. We've just made that story that much better. We feel like a lot of people who are invested in SANs are going to be needing them because they have high-performance workloads out of that. So we've just made the story that much better. So this is going to be a common configuration where you have CSV layered on top of a SAN. That's not changing. The other important configuration that we think is going to be prevalent is having file shares backed by storage spaces. So when you start talking about file share, people automatically start thinking about a reduced cost deployment model. And we feel like the file share, as well as having storage spaces, which uses just a bunch of disks to manufacture storage pooling as well as resiliency attributes, is going to be really useful out there to reduce the cost of storage. But you could also scale this file share configuration if you want with all sorts of hardware like RDMA and using a SAN in the backend of the file share. It's possible. I don't know. There might not be a lot of people who would put SAN behind a file share when they could directly connect to it. But if your organization is something that wants to move that SAN to use for multiple purpose through file shares, that's a possibility. You could also scale out these file servers to 8-node configurations and then generate enough I/O workload in them to use a SAN. That's another possibility where you would take a SAN behind the file share. And the last configuration is something that we feel is going to be a part of the branch office solution, right? Just a basic 2-node Hyper-V cluster with either storage spaces or a clustered PCI RAID system. And the clustered PCI RAID systems that we feel are going to be something that the system builders are going to be using to build cluster-in-a-box solutions. So again, there's another session that talks exclusively about cluster-in-a-box solutions. This is another configuration that we feel that is going to be commonly deployed out in the field. Related content, there's a whole bunch of sessions that talk about Hyper-V, that talk about storage improvements overall in the whole stack. Please definitely go attend them. There's hands-on labs. There's product demo stations. I do have a few more demos. If anybody's interested in seeing them, definitely drop by the virtualization booth and find me for any kind of further talks on virtualization, storage improvements. Definitely come find me there. Please fill out your evaluation forms and submit your evals.